US Physics Olympiad, year 2015, F equal MA. First round. This round consists of 25 problems. It was given 75 minutes for these problems. All solutions for all these problems you can find in the description below of this video. And please subscribe for the channel. In that case, you have chance to get all problems from American and other Olympiads. Problem 1. A 600 meter wide river flows directly through 4 meters per second. A small motor boat travels at 5 meters per second in still water and points in such a direction so that it will travel directly east relative to the land. What is the closest time it takes to cross the river? Problem number 2. A car travels directly north on a straight highway at a constant speed of 80 km per hour for a distance of 25 kilometers. The car then continues directly north at a constant speed of 50 km per hour for a distance of 75 more kilometers. The average speed of the car for the entire journey is closest to. Problem number 3. The force of friction on an airplane in level flight is given by F friction equal kV square, where k is some constant and v is the speed of the airplane. When the power output from the engine is P0, the plane is able to fly at a speed V0. If the power output of the engines is increased by 100% to 2P0, the airplane will be able to fly at a new speed given by. Problem number 4. A 2 kg box is originally at rest on a horizontal surface where the coefficient of static friction between the box and the surface is μs, and the coefficient of the kinetic friction between the box and the surface is μk equal 0.90 μs. An external horizontal force of magnitude P is then applied to the box. Which of the following is a graph of the acceleration of the box A versus the external force P? Problem number 5. A 470 gram lead ball is launched at a 60 degrees angle above the horizontal with an initial speed of 100 meters per second directly toward a target on a vertical cliff wall that is 150 meters away as shown in the figure. Ignoring air friction, by what distance does the lead ball miss the target when it hits the cliff wall? Problem number 6. 3 trolley carts are free to move on a one-dimensional frictionless horizontal track. Cart A has a mass of 1.9 kilograms and an initial speed of 1.7 meters per second to the right. Cart B has a mass of 1.1 kilograms and an initial speed of 2.5 meters per second to the left. Cart C has a mass of 1.3 kilograms and is originally at rest. Collisions between carts A and B are perfectly elastic. Collisions between cart B and C are perfectly inelastic. What is the velocity of the center of mass of the system of the 3 carts after the last collision? Problems 7 and 8. The following information applies to questions 7 and 8. Carts A, B and C are on a long horizontal frictionless track. The masses of the cards are M, 3M and 9M. Originally card B is at rest at the 1 meter mark and card C is at rest on the 2 meters mark. Card A is originally at 0 meter mark, moving toward the card B at a speed of V0. Question 7. Assuming that all collisions are completely inelastic, what is the final speed of card C? Question 8. Assuming that all collisions are completely elastic, what is the final speed of card C? Problems 9 and 10. The following information applies to questions 9 and 10. A 0.65 kg ball moving at 5 meters per second collide with a 0.75 kg ball that is originally at rest. After the collision, the 0.75 kg ball moves off with a speed of 4 meters per second, and the 0.65 kg ball moves off at a right angle to the final direction of motion of the 0.75 kg ball. Question 9. What is the final speed of the 0.65 kg ball? Question 10. Let the change in total kinetic energy in this collision be defined by delta K equal Kf minus Ki, where Kf is the total final kinetic energy and the Ki is the total initial kinetic energy. Which of the following is true? Problem number 11. A sphere floats in water with 2/3 of the volume of the sphere submerged. The sphere is removed and placed in oil that has 3/4 the density of water. If it floats in the oil, what fraction of the sphere would be submerged in the oil? Problems 12 and 13. The following information applies to questions 12 and 13. A pendulum consists of a small block of mass M attached to a fixed point by a string of length L. The pendulum block swings down from rest from an initial angle theta max less than 90 degrees. Question 12. Which of the following statements about the pendulum blob's acceleration is true? Question 13. Consider the pendulum bob when it is at angle theta equal 1/2 theta maximum on the way up, moving toward theta maximum. What is the direction of the acceleration vector? Problems 14 and 15. The following information applies to questions 14 and 15. A 3 meters long massless rod is free to rotate horizontally about its center. Two 5 kg point objects are originally located at the ends of the rod. They are free to slide on the frictionless rod and are kept from flying off the rod by an inflexible massless rope that connects the two objects. Originally, the system is rotating at 4 radians per second. Assume the system is completely frictionless and ignore any concerns about the instability of the system. Question number 14. Calculate the original tension in the rope. Question number 15. The rope is slowly tightened by a small massless motor attached to one of the objects. It is done in such a way as to pull the two objects closer to the center of the rotating rod. How much work is done by the motor in pulling the two objects from the ends of the rod until they are each 0.5 meters from the center of rotation. Problem number 16. Shown below is a graph of potential energy as a function of position for a 0.5 kilogram object. Which of the following statements is not true in the range of from 0 to 6 centimeters? Problem number 17. A flywheel can rotate in order to store kinetic energy. The flywheel is a uniform disc made of material with density ρ and tensile strength sigma, measured in pascals, the radius r and the thickness h. The flywheel is rotating at the maximum possible angular velocity so that it does not break. Which of the following expressions correctly gives the maximum kinetic energy per kilogram that can be stored in the flywheel? Assume that alpha is a dimensionless constant. Problem number 18. Shown below are three graphs of the same data. Which is the correct functional relationship between the data points? Assume A and B are constants.
Problems number 19 and 20. The following information applies to questions 19 and 20. A U-tube manometer consists of a uniform diameter cylindrical tube that is bent into U shape. It is originally filled with water that has a density ρW. The total length of the column of water is L. Ignore surface tension and viscosity. Question 19. The water is displaced slightly so that one side moves up a distance x and the other side lowers a distance x. Find the frequency of the oscillation. Question number 20. Oil with a density half that of water is added to one side of the tube until the total length of oil is equal to the total length of water. Determine the equilibrium height difference between the two sides.
Problem number 21. An object launched vertically upward from the ground with a speed 50 meters per second bounces off of the ground on the return trip with the coefficient of restitution given by CR equal 0.9, meaning that immediately after a bounce the upward speed is 90% of the previous downward speed. The ball continues to bounce like this. What is the total amount of time between when the ball is launched and when it finally comes to a rest? Assume the collision time is 0. The bounce is instantaneous. Treat the problem as ideally classical and ignore any quantum effects that might happen for very small bounces. Problem number 22. A solid ball is released from rest down inclines of various inclination angles theta, but through a fixed vertical height h. The coefficient of static and kinetic friction are both equal to μ. Which of the following graphs best represents the total kinetic energy of the ball at the bottom of the incline is a function of the angle of the incline? Problem number 23. A 2 kilogram object falls from rest a distance 5 meters onto a 6 kilogram object that is supported by a vertical massless spring with a spring constant K equals 72 newtons per meter. The two objects stick together after the collision, which results in the mass spring system oscillating. What is the maximum magnitude of the displacement of the 6 kg object from its original location before it is struck by the falling object? Problem number 24. The speed of a transverse wave on a long cylindrical steel string is given by formula V equals square root from T over M over L, where T is the tension of the string, M is the mass, and L is the length of the string. Ignore any string stiffness and assume that it does not stretch when tightened. Consider two steel strings of the same length, the first with radius R1 and the second thicker string with radius R2 equal 4R1. Each string is tightened to the maximum possible tension without breaking. What is the ratio F1 over F2 of the fundamental frequencies of vibration on the two strings? Problem number 25. Two identical cards A and B, each with mass M, are connected via a spring with a spring constant K. Two additional springs, identical to the first, connect the cards to two fixed points. The cards are free to oscillate under the effect of the springs in one-dimensional frictionless motion. Under suitable initial conditions, the two cards will oscillate in a phase according to this equation, where XA and XB are the locations of cards A and B relative to their respective equilibrium positions. Under other suitable initial conditions, the two cards will oscillate exactly out of phase according to this equation. Determine the ratio omega 2 over omega 1.